Thanks, Chris. So 2 years ago today, I was at ISCA presenting our first generation of MTIA. Now I'm here to introduce our second generation chip, and this time talk about model chip co-design and our experience getting the chip into production. I want to note, while I'm presenting, this is on behalf of a very large cross-functional team at Meta who all really did wonderful work to get this chip into our data centers. So MTIA'25 has been deployed at scale. It's serving billions of users across multiple regions for Meta. This chip is targeting our ranking and recommendation workloads, and for those workloads, we got significant improvements over our first generation, and we're able to lower TCO compared to the latest GPUs by an average of 44% and achieve on-par perf per watt. I want to point out that this is a real solution end-to-end, co-designed, starting with the silicon, the system design, the modules, CPU, DRAM, all customized for our workloads, put in racks in the data center, giving us end-to-end efficiency gains across all our different workloads. So the point of this paper, we decided to do something a little different and not focus as much on the architecture, but really kind of look back and share lessons from our experience getting this chip into production and serving for our family of apps. So I'll talk about how we've co-designed and optimized our models for our MTIA architecture, how we've had to use this solution to support a really wide range of models in production, and some lessons from our productionization experience. So let me set the context a little bit by talking about two things that are kind of unconventional in terms of our MTIA solution. So one is in terms of the workloads we're targeting. So in the ranking recommendation space, we have a really wide set of models, and they're evolving over time, both their size in terms of number of parameters and their complexity, the amount of compute or input we do, continues to grow. You can think of sort of ranking a recommendation as a funnel where you have a retrieval model in the beginning where you're ranking, say, 1 million candidates, and it's very low complexity. And then that goes to an early stage where you might rank like 10,000 candidates, and it's 10x more complex. And then finally, those results are taken to late stage to do the top 100 ranking, and that's another 20x in complexity. But another thing I want to call out, which emerged during the development process of this version of MTIA, was that we started seeing recommendation models with transformer architectures. So HSTU has been a popular one that was developed at Meta. And this, we've used it for both retrieval and ranking, and we have much larger models, and this is yet another order of magnitude more complex than our traditional ranking recommendation models. The other thing I want to point out is that we took an unconventional approach in the design of the MTI hardware, and we built a memory hierarchy that does not have HBM. So we optimized for lower cost and lower power, and we operated under the observation that for our diverse set of workloads, we could capture most of the locality in on-chip SRAM. So we built a large cache, 256 megabytes at 2.7 terabytes a second of bandwidth, and we were able to back it then with LPDDR DRAM at just 200 gigabytes a second. So you can tell this creates an obvious bandwidth gap to go off chip, and so in order to get high efficiency out of MTIA, we have to optimize with that in mind. So I'll just quickly go over the specification for MTIA'25 and want to compare it to our first generation. We moved from 7 nanometer to 5 nanometer TSMC process. We were able to increase the frequency by 1.7x to 1.35 gigahertz. In about 10% more area than our first design, we were able to pack in 2x the number of gates and 1.6x the number of flops. And we were able to increase the TDP for the chip from 35 watts to 85 watts. Am I not close enough? Thank you. Thank you. So, with that extra compute power, we were able to push the peak flops up 3.5x from 50 teraflops a second to 177 teraflops a second of FP16 and BF16. Then in the memory hierarchy, we were able to increase the on-chip SRAM by 2x, provide more than 3x the bandwidth, to better feed the higher peak flops, and we're able to increase the size of the off-chip LPDDR DRAM in order to handle larger and larger parameter models. Here's the MTI-2i architecture at a glance. This is largely inherited from our first generation design, but we were able to get about 3x the performance in roughly 10% larger die size, like I mentioned. We have the same 8x8 grid of processing elements connected via a custom mesh network. And that's connected then to crossbars along the sides of the chip that are connected to the on-chip global SRAM and to 16 channels of LPDDR surrounding it. Then there's a control subsystem and host interface to talk over PCIe, handle requests, and schedule jobs on the PE grid and send responses back to the host. I want to talk just briefly about the PE architecture. This is where a lot of the efficiency gains for sparse and dense operators comes from in MTIA. We have two RISC-V processors, and on the left we have the peripherals attached to them, and then on the right you can see we have this command processor and a set of fixed function units for offloading, computation, and data movement. The way this works is it provides an asynchronous data flow execution model. So you could program the RISC-V cores to basically generate a series of custom instructions and their dependencies, and then the command processor takes that and schedules those operations on the fixed function units. And in that way, you can do DMAs over the fabric interface into the local memory. You can do memory transformations, dot product engine calculations, so matrix multiplies, SIMD calculations, and those can all get overlapped in time. There were a bunch of new features on this chip, a lot of them somewhat speculative, kind of thinking about different ways our models would evolve. I won't go into details, but I do want to point out that we did provide fast eager mode support in hardware on this chip. So since eager mode is a very important feature of PyTorch and very critical to training, we wanted this feature to prototype it for future training chips. And we also found it was critical even for inference models where there are parts of the model that we can't capture with static graph mode compilation, and so we could offload them with eager mode. And the hardware acceleration we did allowed us to have very fast job launch and job completion times. Moving up one step from the silicon to the system, we were able to get to production quickly by building a system that was leveraging the same Grand Teton platform we have for our GPUs. But in this design, we packed in a lot more ASICs because they're a lot smaller. We have 24 ASICs per host, split across 2-socket CPU design, and 3 hosts per rack for a total of 72 ASICs per rack. And this gives us roughly the same flops per watt density as our GPU systems. But in some sense, it's more flexible because we have a finer grained unit of allocation for scheduling jobs. The software stack also evolved for this second generation of MTIA. We still focus primarily on supporting PyTorch, so we have the same developer experience across GPUs and MTIA. We added support for, in the runtime for eager mode, and we upgraded to PyTorch 2.0 so we could leverage Torch Dynamo and Torch Inductor for tracing and for compilation, and we added Triton so we could author kernels in the same way we would for GPUs. So let me talk a little bit about our model chip co-design experience. One of the key aspects was building up a framework to auto-tune models. And why was this important for us? Well, one, we have a large number of small models that make up a large capacity of the fleet, and so it's prohibitive to do all this optimization manually. The other reason this was important is that we built in a lot of configuration knobs into the hardware and up through the software stack in order to tune our models. Some key areas were the following. So one, data placement. So we needed to try to size the activations buffer so that it fit in the scratch memory, the on-chip global SRAM, and then we could use a fraction of that for activations that would be pinned, and then we could use the rest as a last level cache that would be useful for operators like table batched embedding or for storing the weights for large FC layers. We also built a framework for kernel tuning for basically, when we have a new model, being able to pick the optimal variants, particularly for FC kernels based on their shape. And we built up a database and used a nearest neighbor method to do that. And then we had a bunch of parameters at the system level that also needed tuning. So it's important to pick a snapshot of a model at sort of the right batch size so that its working set would fit well in SRAM, to tune the request coalescing we would need to do to kind of get good utilization of that batch size on device, and the sharding parameters of the model. The other thing I'd point out that it was really significant to exploit locality across the stack. So we needed to very carefully think about how we wanted to partition data between the scratch and the LLC. And we could do this in a very fine-grained manner, and so we could pick, certain tensors would want to be pinned, others it would be okay to have them be evicted and written back to memory. There were also a lot of cases where we knew data wasn't going to be used again, and we had a way of providing memory hints to skip those write-backs and improve performance. We did a lot of operator fusions so that we could keep data within the distributed local memory of all the PEs. And we spent a lot of time optimizing gems, particularly ones where we would have large weight tensors that wouldn't naturally fit in SRAM. And so we could do things like prefetch weight tiles into the LLC to help hide the latency of going to DRAM. I won't spend much time here, but I would say you should see the paper for more details. We had a lot of challenges in trying to keep up with the model evolution at Meta. We have models with sequence embeddings, so we had to support jagged tensors, and others. I'd refer you to the paper for that. Also, we ended up with limited use of quantization in production because it ended up being more challenging than we thought, but we continue to work in this area to provide higher performance for our models. So let me talk about a couple lessons from our productionization experience. The first couple are related to deployment. So one is about handling memory errors, and you might think, okay, well, maybe that should just be, open and shut issue, just turn ECC on and be done with it. But since we did use LPDDR to save cost and save power, we had a technology that didn't have built-in ECC support. And so we actually have to compute it in line, and that has a performance hit. So as a result, we decided to sort of defer this decision and do a study as we got more and more silicon into our fleet, look at memory failure rates, and do error injection studies, see which data is most susceptible to errors in terms of affecting model quality, and even look at mitigation techniques in software. But in the end, I think all those things were sort of insufficient to convince us to turn it off, and it was better to just keep it on and instead spend more of our effort optimizing performance to make up that gap. Another important area was providing the capability to have near real-time and very frequent firmware updates. So we're actually able to deploy firmware updates like regular software through continuous CI/CD pipeline. And this is very different from what we have through third-party working with GPUs, right? So in 2024, we had 23 firmware releases for MTIA versus just 1 to 2 updates we'd gotten for our GPUs. And this allowed us to quickly fix some silicon issues that we had as we first deployed the chips into production. And then finally, one of the advantage of doing this all in-house was that we were able to build up a large-scale A/B testing setup on live production. So this was fully automated and a stack that could serve on either or a mix of MTIA and GPUs. And then as a result, we could do these in-production A/B tests where we could look at ads revenue, we could look at latency, throughput, error rate, model quality, and in the end, this was kind of the ultimate measure of our per TCO gains. We were also able to further optimize MTIA and improve efficiency based on testing we could do at scale in production. So one was in terms of overclocking the chip. So we were able to increase frequency from 1.1 gigahertz to 1.35 gigahertz based on a large-scale study we did over thousands and thousands of devices, where we studied, as we changed frequency, measured end-to-end performance and reliability, and prove that this was safe, and then put the monitoring in place to continue to look at this even in production. Another area where we had really big savings was in reducing the provision power. So initially this is done rather conservatively when we do initial stress testing and sort of application load testing early on in the process. And for us, I think the models that we used initially were relatively unoptimized on MTIA. And so after 6 months of production experience, when we'd done a lot of testing in the fleet, we found that we were actually able to reduce that provision power by 40%. And then a final thing is that we found there was a really big advantage to deploying much smaller accelerators compared to GPUs. And part of this had to do with the fact that we have a lot of models in production where we're running experiments, and so traffic is low. And then also there's just a variable amount of load on them. So GPUs can tend to be underutilized, and using smaller devices made it less expensive to have the buffer for those sort of traffic spikes. And so that gave us an additional 90% per TCO gain over sort of standalone replayer testing. So we looked at one of the top 5 recommendation models at Meta in terms of revenue. This model was something we worked with our monetization team on for months, and it evolved. It increased 6x in complexity, and we were able to increase per TCO starting at 0.5x to 1.8x. There were a lot of optimizations across the stack. One I would call out in the serving pipeline here, we end up sharding this model. We have multiple remote networks, the sparse portion. And one thing we had to do was sort of combine or fuse them into fewer nodes so that we reduced the scheduling pressure so that we could meet our latency objective, and that would increase throughput by about 20%. So just to highlight the final results, the top graph here shows a set of models that we've deployed into production, and I want to show that we indeed have, a set of low complexity models and go up to 1,000 megaflops a sample for high complexity models. We demonstrate per TCO and per watt gains against our GPU baseline. In general, we did better on models where we could more easily fit the working set in SRAM, but the results here also depended on how much effort we put into optimizing them. So just to wrap up, I want to talk about some of the challenges and opportunities for MTIA going forward. So you probably noticed I didn't mention LLMs at all. When we designed this chip, ChatGPT and Llama were not a thing yet. And so, we're actively working in this area for future MTIA. Even ranking and recommendation models continue to grow in complexity. And so that's one limitation here, that as they grow, this is going to hit that latency SLA faster. And then finally, we have a maturing, really young software ecosystem that we have to continue to improve to be effective at scale and on the latest models. So please stay tuned for future generations of MTIA. Thanks.
Thank you.